All right, good morning, everybody. Today is day 5, and we're going to cover again 2 sections, but these should be pretty small sections, so it's not going to be as big as Fridays. Our first section is going to be 2.1, the idea of limits, and it might seem a little counterintuitive that we just did all this work to finish up chapter 2, and now we're going back to the introduction, but you'll see why once we get to chapter 3, section 3.1, which is going to be the next video. So first of all, we're going to borrow a lot of ideas from physics to start with, and whether or not you've taken a physics class, whether or not you've taken a physics class based with calculus, it doesn't really matter. Hopefully I'll be able to introduce all of the ideas that we need, and you'll be able to feel comfortable with them by the end of the presentation. So our first idea is average velocity. Suppose you are super bored and you want to calculate your average velocity, otherwise known as your speed, as you travel along a very straight highway, think I-80. If you pass mile marker 100 at noon and mile marker 130 at 12:30 p.m., you've traveled 30 miles in half of an hour. Your average velocity, or your speed, over this time interval is 30 miles divided by half an hour, or 60 miles per hour. That's below the speed limit. Make sure you're obeying all traffic laws if you're doing something like this. Anyway, by contrast, even though your average velocity might be 60 miles an hour, it's almost certain that the speed indicated by your speedometer, your instantaneous velocity, varies from one moment to the next. So maybe for a couple minutes you're going 65 miles an hour, or maybe you're going 70 miles an hour. Maybe you're really breaking the law and you're going 100 miles an hour, but then you hit some traffic, you have to slow down. So at any given moment, your speedometer could say any value. But because it took you 30 minutes total to travel 30 miles, overall, you're traveling at 60 miles an hour. So in this regard, your average velocity, or your speed, is different than your instantaneous velocity. And in calculus, we're interested in this idea of instantaneous velocity. So let's start with an example. A rock is launched, and we're stealing a bunch of things from physics, so don't worry if you've never seen anything like this before. But a rock is launched vertically upward from the ground with a speed of 96 feet per second, which is pretty quick. We borrow an equation from physics that states the position of the rock after t seconds, which is s of t equals negative 16t squared plus 96t. And I'm going to call this equation 1. Your position, s, is measured in feet with S0 equals the ground. So S1 would be 1 foot above the ground, S10 would be 10 feet above the ground. We're interested in finding the average velocity between t equals 1 seconds and t equals 3 seconds. So unlike previous examples, we're just going to dive right into the solution. You don't have to pause here. To borrow another equation from physics, the average velocity of your rock over any time interval, t0 to t1, looks like this equation where we've got the average velocity equals the position at t equals 1 minus the position at t0 all over t1 minus t0. For us, t0 equals 1 and t1 equals 3. So we plug those values into our equation 1 from the previous slide. The average velocity over the time interval 1, 3 is velocity subscript average, I've shortened things because I'm lazy, equals s of 3 minus s of 1 divided by 3 minus 1. When you plug everything in, you get that s of 3 equals 144 feet, while s of 1 equals 80 feet. So we have 144 feet minus 80 feet divided by 3 minus 1. That equals 64 feet divided by 2 seconds, which equals 32 feet per second. And that's how we find the average velocity over a time interval. And here's an important observation. The average velocity is the slope of the line joining the points 1, S1 and 3, S of 3 on the graph of the position function. So I've included this graph, and hopefully I can walk you through it so that you understand what we're going with. So this point down here is 1, S of 1. And this point over here is 3, S of 3. So we have 3, 144, and 180. And we get this nice straight line. You only need 2 points to create a straight line. And it's intersecting our curve at 2 points, the 2 points that we picked out in the first place. So the velocity is the slope of these two lines. We have rise over run, so we rose 64 feet, and our run, we moved over 2 seconds. So 64 divided by 2 seconds equals 32 feet per second. And that exactly works out the way you expect it to. So we just computed a line passing through a curve at 2 points. And any line that behaves like this is called a secant line. This is important for you to know just based on lines and stuff like that. So like a chord, arc length, all the sort of stuff that you would have learned in a pre-calculus class like trig or algebra, all of that stuff is coming back to visit us. But any line that passes through a curve at exactly 2 points is called a secant line. But what about a curve passing through a line at just 1 point? Well, that sort of line is called a tangent line, and calculus is very interested in lines like that. So let's walk through this diagram. I have 4 identical curves. I know because I copied them that way. And we have our curve, and we have a point X, and we have a point A. And through X and A, their evaluations, we have a line that passes through them. And if I move X close to A, my slope gets a little steeper. And when I move X towards A a little bit again, my slope again gets a little steeper, and my 2 points are pretty near. And when I move X to equal A, now I've got a tangent line. So I had secant lines that were getting steeper and steeper and steeper, and then I ended up with a tangent line once X equals A. So what did I just do? I just took a limit, which is exactly what we've been doing and what we're familiar with. So I'm suggesting that we can compute the instantaneous velocity by just taking the limit as X approaches A of our average velocity. So the limit of a position of X minus the position of A divided by X minus A as X approaches A. So once we strip away all of the physics, computing the instantaneous velocity is the exact same as computing the slope of the tangent line. So we've already computed the slope of the secant line, and now we want to move X to equal A, take that limit to get the slope of the tangent line. So here's an example of instantaneous velocity. Find the slope of the line tangent to the graph of f of x equals x squared plus 2x minus 8 at a point 1, comma, minus 5. So for this one, go ahead and pause, maybe scroll back up through the presentation, which I've posted, and see how far you can get. It doesn't matter if you solve it all the way, just matters that you gave it a try. Get those brain juices flowing. So welcome back from our pause. We're going to use the definition of slope of a tangent line and let A equal 1. So I have a typo here. I'll fix that before I post these slides. So M is going to represent our slope, just like you do in y equals mx plus b. M subscript tangent. So I'm looking for the slope of the tangent line. And this is going to be the limit as x approaches 1 of a function f of x minus f of 1 divided by x minus 1. So I plug in all my values, and my original f of 1 value is -5. So a negative times a negative equals positive. That's why we get that plus 5 right there. So we have x squared plus 2x minus 8. That's our function, plus 5 all over x minus 1. We can simplify and get x squared plus 2x minus 3 over x minus 1. And when we factor our polynomial on top, we get x plus 3 times x minus 1. Well, my x minus 1s are going to cancel, so then I'm just left with the limit as x approaches 1 of x plus 3, and that's going to equal 4. So the slope of my tangent line in this case is 4. And that's going to be it for today's presentation. Or for this presentation, I should say. I shouldn't say today's presentation.